Hey there, long time no see. Welcome back to the channel. I'm absolutely thrilled today because I've got some exciting news to share. I won second place in the Lelapa AI challenge. And in this video, episode 5 of our series, I'm going to give you a quick walkthrough how I did it. More in-depth explanations will follow in the upcoming episodes, where we'll break down each step and dive into the details. If you've been following along, you know we've been on quite the journey. We started by exploring QLoRa for efficient fine-tuning on small models, then figured out how to balance loss across different tasks, dove into zero-shot inference with Gemma 4B, and tackled full parameter fine-tuning while solving those pesky out-of-memory issues on T4 GPUs. Today, we're putting it all together with the winning strategy. The best part, this solution is end-to-end implemented and executed on Kaggle notebooks, which is free and reproducible. My solution combines data synthesis and full fine-tuning with two key models, Google's Gemini and the competition-mandated InkubaLM. So what exactly was this challenge about? Well, Zindi's Lelapa AI Buzuzu Mavi challenge asked us to build a robust model that could handle 3 different NLP tasks across 2 African languages, Swahili and Hausa. The tasks were sentiment analysis, determining if text is positive, neutral, or negative, natural language inference, figuring out if one statement logically follows from another, and machine translation, translating English to either Swahili or Hausa. Here's the kicker: we had to use a specific base model called InkubaLM 0.4b, and the really challenging part? Extreme data scarcity. We only had about 1,400 labeled samples across all tasks and languages combined. That's practically nothing in the world of modern NLP. So my core strategy became, how can I aggressively augment this tiny dataset? The answer was to leverage Google's Gemini API for data generation and reasoning, then perform full fine-tuning of InkubaLM. You might wonder why I don't use Gemma or other open-source models. One fun fact is I run out of Kaggle GPU credits, which is 30 hours per week, so I have to look for alternatives without GPU. Let's see how that worked out. I approached this challenge with a 5-step strategy that turned out to be the key to success. First, data synthesis. I used Gemini to paraphrase existing inputs, expanding the training data size by 10 times. If you're working with limited data, this is absolutely crucial. Second, I did training data analysis. I had Gemini generate explanations for the original labels, creating rich examples that would be valuable for the next step. Third came synthetic data labeling. I used Gemini again with a technique called guided many-shot prompting to generate high-quality labels for all that synthetic data. Fourth was the InkubaLM fine-tuning, full parameter fine-tuning on the combined dataset of original plus synthetic data. And finally, I implemented efficient inference, batched prediction using the fine-tuned model. A couple of key technologies made this possible: Google Gemini Flash 2, InkubaLM 0.4b, and Hugging Face's transformers and TRL libraries. Oh, and I need to highlight why Gemini API was such a game-changer here. Beyond its state-of-the-art generative capabilities, it has an extremely generous free tier, 1 million token context window, and 1,500 requests per day. That's potentially billions of tokens per day for free. This was perfect for the kind of data generation I needed to do. Now let's dig into step 1, data synthesis through paraphrasing. The goal was simple: massively increase my input data volume and diversity. I used Gemini to paraphrase the original training and test inputs across all tasks. For sentiment analysis, I paraphrased the inputs. For NLI, I paraphrased both the premise and inputs. And for machine translation, I paraphrased the inputs. Here's a peek at my system prompt to Gemini and a quick example of paraphrasing. It should be noted that I asked Gemini to output structured JSON format. If you're interested in the details, I've shared my full data synthesis notebook on Kaggle. The link is in the description. Step 2 was training data analysis, where I generated explanations for the original labels. The goal here was to understand why the original labels were correct for sentiment analysis and NLI tasks, so I could create high-quality labels for the synthetic data. I used Gemini to analyze input label pairs and explain the reasoning, comparing against alternatives. Here's what my system prompt looked like for NLI and an example with analysis generated by Gemini. These rich explanations became valuable context for the next step. Now for step 3, synthetic data labeling through guided many-shot prompting. The goal was to assign accurate labels to all that paraphrased data from step 1. I used Gemini with many-shot prompting, providing numerous high-quality examples, including those explanations from step 2, to guide Gemini's predictions. What's great about this approach is that by providing those examples with detailed analyses, Gemini not only gives us labels, but also explains its reasoning before the final answer. This is a powerful technique known as chain of thought prompting. It also helps us verify the quality of the synthetic labels. For instance, when given a Hausa pair about educated communities, Gemini correctly labeled it as false and provided a detailed analysis explaining the contradiction between the premise and hypothesis. Step 4 was where everything came together, full fine-tuning of the InkubaLM 0.4b model. The goal was to adapt this required model using our augmented dataset. I used full parameter fine-tuning, adjusting all weights for deeper adaptation. A few key implementation details. I combined the original labeled data with the Gemini-labeled synthetic data. I implemented target length balancing. This was critical. I repeated short targets like positive about 11 times to match the average machine translation target length, preventing bias toward short outputs. I used consistent instruction prompting format across all tasks. For training, I used TRL SFT Trainer with completion only lost to focus learning only on generating the response part. To avoid the out-of-memory error, I used Atom W8-bit for optimizer. This fine-tuning approach allowed the model to effectively learn from our expanded dataset and handle all 3 tasks across both languages. The notebook with all implementation details is linked below. Step 5 was inference, generating predictions quickly and accurately. I loaded the best fine-tuned checkpoint and performed batched inference across both available GPUs. For model loading, I use Float 16 format with automatic multi-GPU distribution and memory efficiency. The inference is batched, 16 samples per batch, for significant speedup. I turned off sampling for deterministic output. The entire inference only takes 104 seconds to generate the full submission. It's lightning fast. For post-processing, I decoded outputs, extracted the generated text after the prompt, and converted to the required submission format. And the result? Second place with a private leaderboard score of 0.529. Looking back, there were a few key success factors. Gemini API was absolutely crucial for overcoming data scarcity through intelligent synthesis and guided labeling. Full fine-tuning allowed InkubaLM 0.4b to effectively learn the multitask, multilingual requirements from our augmented data. The target length balancing technique likely improved stability and performance across tasks, and efficient implementation made the whole approach feasible. The takeaway? This hybrid strategy, using a powerful foundation model like Gemini for data augmentation and reasoning, combined with targeted full fine-tuning of a smaller required model like InkubaLM, is incredibly effective for tackling low-resource NLP challenges. If you're working with limited data in your NLP projects, this approach could be a game-changer. As promised, all my Kaggle notebooks are available for you to replicate this approach. I've created notebooks for each step: data synthesis, data analysis, generating labels, full fine-tuning, and inference. The links are all in the description below. I've also included links to the Google Gemini API documentation and the competition page if you want to learn more. And that wraps up our journey through my second-place solution for the Lelapa AI challenge. I hope you found this walkthrough valuable and picked up some techniques you can apply to your own NLP projects and competitions. If you enjoyed this video, please subscribe to the channel for more content on data science, machine learning, and AI competitions. Drop a comment below if you have any questions or if there's a specific aspect of this solution you'd like me to explore further. In the next episode, I'll explain the details of how to use Gemini API to do large-scale data generation effectively. Thanks for watching, and I'll see you in the next one. Happy modeling!